Let us observe the motion of an object and record the information about its position with respect to time. What we have got here is called the position-time graph of our object's motion. Though it is not the actual path followed by the object, but it contains a lot more information about its motion. First of all, from this graph, we can say that for the complete motion of the object, the net displacement is equal to this, and the total time of motion is equal to this. So we can say that the average velocity of the motion will be equal to delta x by delta t. Note that if we join the initial and final points of motion, then we can say that the slope of this line, that is, tan theta, is equal to delta x by delta t, which is equal to the average velocity. This means that the slope of the line between any 2 points on the position-time graph is equal to the average velocity in that time interval. But what about the instantaneous velocity? As we know that if we shrink the time interval such that it is infinitely small, then this line becomes a tangent at that point in the position-time graph. So the slope of the tangent at any point in the position-time graph gives us the value of instantaneous velocity at that point. From calculus, we know that for any function, its first derivative is equal to the slope of the function at any point. As velocity is the first derivative of position, so it is expected that velocity should be equal to the slope of the position-time graph. This is consistent with our observation. Note that for these points, the tangent is a horizontal line which has a slope equal to 0. This should mean that the velocity of the particle at these points will be equal to 0. That is, the particle should be at rest, which is true as per its motion. So, a horizontal section in the position-time graph implies that the particle is at rest. Also note that at all these points, the tangent has the same slope. This means the velocity at all these points should be the same. So a straight line in position-time graph means that the particle is moving with constant velocity. This can be verified, as in the equal intervals of time, the displacement of the particle is equal. If we calculate the average velocity in this region, it will be the same as the instantaneous velocity. Whenever the particle is moving with constant or same velocity, its average and instantaneous velocities are equal. Such a motion is called uniform motion. Now, for this curved region, we can see that the slope of the tangent is increasing. So we can say that the velocity of the particle must be increasing in this region. This is expected, as our particle was initially at rest, so it must accelerate to gain some velocity. Similarly, for this curved region, the slope of the tangent is decreasing, so the velocity of the particle must be decreasing. This is also expected, as the particle was moving with some velocity, and finally comes to rest, so its velocity should decrease. Thus we can say that the curved regions in the position-time graph represent acceleration or varying velocity. However, we cannot say that the acceleration is constant or not, because for both constant and varying acceleration, we will get a curve in the position-time graph